Okay, off we go. So, real quick, apologies in advance. I've got allergy issues. I am not sick. I'm fairly certain. Allergy meds are helping tremendously, but I apologies in advance for coughs or sneezes that might interrupt the lecture. Okay, so here's where we're picking up from last time. We finished section 1.4. 1.5, we're going to go through pretty quickly. Again, with the tough choices. Right, there's so much we have to talk about in this course. When we get to chapters 6 and 7, you will appreciate the extra time that we will have because that material is quite a bit more substantial and challenging and complicated, etc. So moving as fast as we are is all very deliberate and I think really well advised. Okay, here's what we're going to talk about real quick. Suppose you have a plane. You want to write the equation for a plane. And the things you know about the plane are you know a vector perpendicular to the plane and you know a point in the plane. All right, so this is what I'm going to say defines the plane we're interested in. All right, you give me a point, you give me what we're going to call a normal vector perpendicular to the plane. There is only one such plane. Okay. Now the question is, how can we write the equation of this plane? And of course, for whatever it's worth, while this does describe the plane, it's not computationally particularly convenient if you want to know what points are in this plane. Right? So we're looking for an equation, aka a test. So in particular, some point that may be in the plane or possibly not in the plane. We're not sure, right? What would be the test? How would I look at a point that is or isn't in the plane, compare it to the information that I have about the plane, and what is the test? So there's a couple different ways to write this. I think the first nice way to write this is to say, well, I want to look at that difference vector, r minus r naught. Notice if r is in the plane, then that will be parallel to the plane. And that's an if and only if, right? If r is not in the plane, then that won't be parallel to the plane. Now that's a test of sorts, but here's the problem there. That's not very computationally convenient either. Right? What's our test for whether some vector is parallel to some plane? We don't have a pre-existing such test. Here's another way to phrase the same thing. That vector being parallel to the plane is simultaneous with that vector being perpendicular to that vector. And let me asterisk, I'm being sloppy with the language a little bit. Let's clean up the mess in a minute. But parallel to the plane means perpendicular to the normal vector. Is everybody kind of broad stroke by it? Okay. So, conveniently, we have a nice test for perpendicular. Again, asterisk, apologies. Okay. So, you write that down and, you can sort of redistribute the algebra a little bit, and this is typically considered, this is my favorite equation to describe the plane. And do keep in mind, a lot of this is given, right? So, let me, do it like that. Okay, let me do this. I'll tell you what I'm going to do. I'm going to do this in green. This is the equation of the plane that we were talking about. So, keep in mind, n is known, given. That was one of the defining features of the plane. We have to know what n is. So that's given. That's given. R naught also is a given defining feature of the plane. So that's given too. So this plays the role of being a test. Plays the role of being a test in the sense that whatever point you want to test, you put it right there. The equation works, it's in the plane. The equation doesn't work, it's not in the plane. Is that cool? Yes.
What is R again? Just a vector?
R is it's sort of generic notation for some point we're trying to understand X, Y, Z. Okay, let's get to the asterisk. What was the deal with the asterisk? Y'all remember I made a big deal about how perpendicular and orthogonal are not the same thing. You got to be careful because one makes perfect sense regarding the zero vector. The other makes no sense at all regarding the zero vector. And you may have noticed that in this process, I started very much with the idea of perpendicularity, right? This is a geometric suggestion here. And yet we end with an algebraic, namely orthogonality. So we definitely swept some stuff under the rug there, and we gotta clean up and address that matter. So the difference comes up when one of these vectors is 0. So let's just ask, which of these vectors could be 0, and what do we feel about that? This normal vector? Can that be the 0 vector? No. Its job is to point in a direction to help me understand how the plane is sort of oriented in space. So that's never going to be the 0 vector. Okay, what about this? Right, keeping in mind that's that difference right there. Can that vector be the 0 vector? And if so, what do I think about that? And how do we want do we want the yay or nay on when that's the 0 vector? Well, if this is the 0 vector, then the point that we're testing is R0, which is not only in the plane, it was given to be in the plane. So the test had better be positive there. So not only is it okay to rewrite this as orthogonal, we have to rewrite this as orthogonal. If I require these vectors to be perpendicular, R0 itself would fail the test. So that's why that's one of the reasons, I guess you could say, why we like sort of this form better, or more to the point, this form. Is everybody on board? All right, of course, the normal vector n will have coordinates, let's call them A, B, C. You can take this dot product, and you can see how the normal vector's coefficients are dotting with x, y, z's. Oh, let's see here. I'll use green. X, y, z's coefficients, or x, y, and z. So that's where that comes from. And so there's a couple of takeaways. Just, tools for your toolbox. If you know the normal vector, or I should say, if you know any normal vector for your plane, you already know most of the equation. Whatever that normal vector is, A, B, C, yeah, that's your coefficient. And you can turn that around. And I think this is arguably the cooler trick. If somebody comes to you with an equation and says, hey, here's the equation of my plane, then you can just take these coefficients, just peel them off and say, you know what, that's A comma B comma C is a vector that is perpendicular to that plane. Pretty sweet. Okay. All right. So let's do a quick one. This example falls into a category that I like to describe as puzzles. Sometimes we're defining objects, sometimes we're creating tools, sometimes we're using those tools to solve problems. And the problems that come up in this kind of stuff tend to have sort of a puzzle aspect to them. Namely, I've got some things and I want to produce some other things, and what's the clever little move, and how do I use what tools how do I get there from here, right? This is the little puzzle. So the puzzle here is that we're going to be given, let's see here, we're going to be given 3 points that are in the plane. Notice I am not going to give you the vector perpendicular to the plane. I'm not going to give you your normal vector that you need. Right? Can you find the equation of the plane? So that's the puzzle, as it were. There's various different of these puzzles. In fact, there's dozens and there's endless almost variations of this kind of puzzle where you get some information and then you have to use tools to create the information that you actually need, right? So we're not going to go through all of them, obviously. But so you want to identify unambiguously in your mind, wait a minute, what do I have to work with? What have I been given here? And then also identify in your mind, wait a minute, what do I need? right? What have I been asked? I've been asked to produce the equation of the plane. Okay, so what do I need to make the equation of the plane? Right? So we've been given these 3 points in the plane. We want to produce the equation. The equation, let's see, we recall the equation requires having a normal vector and a point in the plane. We already have a point in the plane. We have 3 of them. We are flush in points in the plane. But we need a normal vector. So I have what's in green. I want what's in blue. The puzzle begins. How do I get from these 3 points to this blue vector perpendicular to the plane? And the clever move here. Oh yeah, sure. Go ahead. Yeah.
Where's it? Oh, say what you do. You have to
If you
set
like,
it
yeah.
equal to 0.
One more time.
You have to set it equal to 0. So you have to find x, y, and z values and dot product with a, b, or c. That.
Well, tempting. So yeah, one thing you could do is you could write down a system of equations, right? So we've got 3 points that the equation has to work for, right? You could do that. There is an easier way, though. So the easier way, the nice, what I'm going to call clever trick in this case, is to notice that if you have points in the plane, then you can subtract pairwise to make vectors parallel to the plane. And if you have 2 vectors parallel to the plane, if only we could find a vector perpendicular to those 2 vectors. Oh, cross product then is going to produce a vector perpendicular to those 2 parallel vectors, and therefore a vector perpendicular to the plane. Did everybody see the slick move? Now your way would have totally worked. I think this is slicker and quicker. Yeah. Okay.
Could you do it?
Do what?
Could you actually tell us what?
Oh no, that's what y'all can. That's arithmetic. Y'all can do the arithmetic, right? So it's just you literally subtract the vectors. You literally do the Christ formulas, right? Yeah. So I want to focus on big picture ideas here. So that's that. This is the way you solve the puzzle. Yes.
I'm confused. Since R naught is one of the A, B, or C, right? Then what's R in the general equation in this case?
Well, I had a little trouble hearing
If
you.
R naught has A, B, or C, what's R N dot R and
Yeah, so R is the point you're testing. So remember, an equation is a test.
Oh.
And whatever it is that you're testing, that's what goes into where R is. Right. Does that satisfy?
Okay.
I mean, because if you're going to test something, right? Like imagine if I have a diamond tester. You know, they have these machines. You can put a stone in, it'll say if it's a diamond or not, right? They don't actually always work. But anyway, you got to have a place to put the thing in that you're testing. That's what R is.
So this question is find equations N dot A equals N dot whatever, just R, arbitrary R, or...
Well, I'm sorry, just one more time.
If, say I get a normal vector from this, on that, right?
Yeah.
So, it's a find equation, I substitute R for an arbitrary value of R, and R naught is A, B, or C.
R is going to be X comma Y comma Z. I mean, it's just understood. I mean, that's what R is, right? If you look back into the it's first few pages of the notes as a standard notation. X, Y, Z. We just shortcut it. We streamline it by just calling it the R vector.
Okay.
Yeah. Right. Okay. Here's a cool fact. Oh yes. Sorry.
One more question. The last thing. Why would R not be A, B, or C and not B minus A or C minus A?
So you have to distinguish between a point and a vector. Right? Now we have this sort of one-to-one correspondence, and it's convenient if you stick to that correspondence strictly, then it is kind of convenient to talk about the point and its related vector, and the vector corresponds to a point. That's nice in certain ways, but nevertheless they are different things. And a vector that is parallel to the plane does not correlate to a point that is in the plane. Right? So that's the big difference here. So let me so let's suppose that the origin perhaps is here. Right? Let's just say. Then if I talk about this point as being a point in the plane, well, thought of as a vector, it's a vector like that. That vector is not parallel to the plane. Does that make sense?
Yeah.
Yeah. And then, okay, let's take it the other way. Here's a vector that's parallel to the plane. Now you got to resist the urge. Lots of students feel this compulsion to say that that vector is in the plane. It is absolutely not in the plane. The vector doesn't even have a location, right? Vectors don't have locations. The only way in which we can make any sense out of a vector having a location, would you mean the point associated to the vector? Because the point associated to the vector is down here. And again, not in the plane. So yeah, so that distinction is very important. Does that make sense?
So when you dot n with r and r0, you're dotting with the vector associated with the point.
Dots are always vectors. Yeah, dots are always between two vectors. That's right. Okay. Yeah.
Yeah, I'm just a little bit still confused about the equation for the plane.
Okay.
It says it's so for some normal vector to the plane n, dot product of r.
Uh-huh.
That's r is a point.
R is a point that we want to be able to test. Keep in mind that when you say equation, that means test. And so R is the thing we're testing.
Okay, so let's say I just want to see this fully fleshed out in example. So let's say we go back to our example here, and then we find some vector ABC as our normal vector.
This sounds like it might be a good thing for office hours. Let's talk about. I mean, we'll go through all the details you want, right? Just come on into office hours. Yeah, absolutely. Okay. So now this is an interesting twist. I think this is a really useful result. I don't see it written down in textbooks very much, but it comes up. It's very handy in a lot of circumstances, and we're going to make significant use of this ourselves later in the class in various examples. If you have an equation for a plane, let's say like this, and if there are no y's in that equation, so you see right here, for example, the y coefficient is 0. I only wrote the 0y to emphasize explicitly that there are no y's in that equation, right? So there's no y's in that equation. Knowing only that, I can instantly conclude that plane is parallel to the y-axis. And it's a lovely little observation. This is handy in a lot of cases. You don't even have to, once you know the theorem and once you've thought through the process, you get to use it for free after that. So let's think through the reasoning. I think this is really nice. If we take, let's see here, take our equation. Now, we know that if you look at these coefficients, that instantly tells us our normal vector. Right? That was one of our takeaways from the previous page. You have an equation, boom, normal vector. That normal vector, notice, has a 0 in a critical location. And that means that the dot product with E2, let's see that bad color choice. If I were to, here we go. If I were to look at E2, keep in mind that E2 is 0, 1, 0. Because of that 0 in that critical location, this dot product's always going to be 0, which means that vector and E2 will always be perpendicular. And if you think about it, now again, geometric appeal, there's going to be a lot of geometric appeal in this class. It's very geometric stuff. If the normal vector is perpendicular to the y-axis, then the plane has to be parallel to the y-axis. Right? You just got to think through what does it look like if your normal vector, right, is, let's say that's the y. Oh, there's the y-axis, right? If my normal vector moves in the ways that keep it perpendicular to the y-axis, then the plane always stays parallel to the y-axis. So, really nice conclusion. I love it when stuff like this comes together, where you have a very simple premise to check. Just look and see, are there any y's in the equation, right? That's all you got to do. And then you get a significant punchline, right? It's like a low cost, it's like a really inexpensive, very valuable product that you can go in the store and buy. It's awesome. You should stock up. Yeah.
Does it only work for Y?
No, great question. It works for any axis. And so this would be a great exercise. I encourage everybody to give it a try. Think through what would the equivalent statement be for the x-axis, for the z-axis. Think through how would you make the corresponding argument. And yes, they all three work. X, Y, or Z. Okay, cool fact. Here's another little puzzle. So we are given a couple of equations of planes. And we are also given a point. I'll do this in dark blue. And what I'm asked to find is not just the line that goes through the point that's parallel to those planes, but I want to specifically make a parametrization specifically, right? Not symmetric equations or not any other description. I want a parametrization specifically of that line. So again, I like to come at these sort of from both ends. I want to take what I'm given and think about what geometrically does that mean I have to work with. I want to take my goal and kind of work backwards. Okay, what geometrically would I need to get to that goal? And when I get there, geometrically, in effect, I am given these two normal vectors that come from these equations. Right? And what do I need? Well, let's see. I want a parameterization. I already have the base point. All I need is a direction vector. And now again begins the puzzle. And by the way, there's only so many tools to work with, and so in some sense, once you know what you're starting with and you know what you're trying to produce, you got a limited set of tools. One of them is the cross product. If you have two vectors to work with, maybe just in case, go ahead and think about whether the cross product might be useful. And here, again, perfect. It's exactly what we needed. We have two vectors that are perpendicular to planes that are parallel to what we're looking for. So, geometric appeal, what we're looking for needs to be perpendicular to these two vectors. Is that cool? Geometrically satisfying? So again, with the cross product, we're going to take these two normal vectors and we're going to cross them to get our direction vector. Okay, again, there's millions of these kinds of little puzzles. Okay, and I do have a warning for y'all. I will point out that one of the aspects of the sort of geometric appeal that I made here is what I'm going to call a transitivity of sorts. It's an abuse of the term, I'm sorry, but the big idea of what I'm claiming is I started knowing that P and N are perpendicular, and then I showed that N and the y-axis are perpendicular, and then from that I sort of connected the dots, as it were, to conclude something about the relationship between the plane and the y-axis. So this connected to that connected to this, and between the two of them I drew a conclusion that I wanted. So likewise with this other question, I started with these two vectors, and I know that they are perpendicular to the planes, and I know that the planes are parallel to the line, and therefore the vector I'm interested in, and again, sort of a transitivity. The normals relate to the planes relate to the vectors, connect the dots, and I draw a conclusion about how these normals connect to that vector. So these kind of transitivities, be careful. Think it through. Really rely on your geometric intuition, because, give me 2 seconds, okay? They really are dangerous. Not everything that sounds like it ought to work necessarily works. And just for your entertainment, here's a couple of easy ones. Here, this vector is parallel to the plane, and the plane is parallel to the other vector. Doesn't it feel like I ought to be able to relate these to each other somehow? And the answer is nope, not even close. Right? B and W don't have to be parallel. They don't have to be perpendicular. They don't have to be anything. Who knows? Right? On the symbolically, if you just look at what's in blue here, it's going to be really tempting to draw a false conclusion. Likewise, down here with planes, P and Q are perpendicular, Q and R are perpendicular, and it's tempting, again, just looking at the way that's written on the page, P is perpendicular to Q, Q is perpendicular to R. Golly, it feels like P and R ought to be maybe parallel or something, but nope. Check it out. These P and R, both perpendicular to Q. Who knows? They could be parallel, they could be perpendicular, they could be neither. No conclusion. So again, you got to be really careful. Any transitivity type argument that you use, there's too many different variations of this to enumerate a complete list, so we're not going to do that. Right? So just make sure to think it through and make sure that you're right. And that's going to be the course policy, by the way. You don't have to cite theorems, and I'm not going to give you said theorems. You just have to be right. That's all. So make sure to think it through. Right? Geometric intuition, we can't get away from. I'm sorry, you had a question.
I was just curious, does this work in all? Is this only the transitivity working in R3, or does it work in
there's various different questions. That's right. So, for example, if you think about vectors being perpendicular, if you're in 3 dimensions, A perpendicular to B, B perpendicular to C, no conclusion.
Yeah.
If you're in 2 dimensions, A perpendicular to B, B perpendicular to C, then A and C have to be parallel. So yeah, it is dimensionally dependent, and so yeah. So you just gotta always keep that kind of thing in mind as well. Okay. Yeah, totally. All right, moving along. This should be kind of familiar, perhaps, right? You all had a homework exercise in section 1.1 or 1.2, somewhere along in there, really early, where you've kind of already done this, and the observation I'm going to make here is that this construction that you put together for that homework exercise, in fact, is the bones of what we call a parametrized surface. Right? So here we're only going to talk about parametric planes. We will later talk about general parametric surfaces. They're going to be an important tool. So this is just kind of our first starter example. But if what you know about a plane is that you have a point in the plane and a couple of vectors parallel to the plane, and you want to use them to generate, not to test, right? We're looking to parameterize. Parameterizations are point generators, not point testers. How would I use these given green objects to produce points in the plane? In particular, all of the points in the plane. And I think it's a pretty easy pitch that you kind of put them together like this, your A and your V and your W. And in some sense, S tells you how far you want to kind of go in that direction. You know what I mean? I mean, the bigger S is, the more you go that way. And the bigger T is, the more you go that way. And so 2 parameters, S and T, will allow you to get anywhere on this plane. Yeah?
How do you ensure you don't get too far away? Because if it's parallel.
One more time.
How do you ensure that it doesn't come off the plane?
That's a great question. Planes are hard to draw because they're infinite. Right? How do I draw? If you think about it, if I were to draw every point in the plane, I would just have an entirely black sheet of screen, right? So when we draw a plane, what we typically draw, I thought I had a piece of paper lying around here. I'm sorry, I don't have paper. But what we typically do is we draw what would a rectangular subset of the plane look like. Now, it's not a law, but very often it's a convenient way to draw a plane. So even though you're right, I drew a parallelogram looking thing, right? The intention was this is supposed to communicate, okay, yeah, but I'm talking about the plane that extends infinitely, that's, parallel to this. Does that make sense? It's just artistically, I don't know a better way. with without computer graphics or something like that. Yeah. So S&T, no constraints on S&T because the plane extends infinitely. Yeah. Okay. All right. So easy example. We'll start with the same givens we had in one of our earlier examples. Suppose I have 3 points, and the goal is not to find the equation. Again, we want to distinguish between parameterizations and equations. How do I parameterize? Well, we use the construction we just talked about. All we need is a couple of vectors parallel to the plane. And again, pairwise subtraction will do that. Yep.
Yeah, just a quick question. Not super relevant to this example, but for inclusion of the plane, it's like 3x plus 2y plus 4z,
Okay.
and then equals some constant. How do you get that constant on the right side?
Yeah, so that constant on the right hand side is that.
Okay.
Yep. So yeah, if you know the normal vector and some point in the plane, dot them. That will give you your d. Yeah.
So like kind of any point.
Any point, they'll all give you the same d. Yeah. Absolutely. Yep. All right. Okay, so very plug and chug, very kind of a rip-off of our last example, arguably easier than our last example, because I didn't even have to find the normal vector. I didn't even have to cross these things. Just pairwise subtract. Those are your 2 direction vectors. Plug it in. So, nice easy example. Okay, there's several discussions in the book about what we'll call distance problems, various sort of questions. How far is this point from this line? How far is what's the distance between 2 parallel planes? What's the distance between 2 skew lines? Right, skew meaning that they're not parallel and they don't intersect. So they're just basically 2 random lines that don't have anything in common, right? How do you find the distance between those lines? How do you find the distance between these planes? These are all, cute little tricks. I've written here what I think are the bones, the outline of the strategy of how to answer a few of these types of questions. So I think it's a healthy exercise to look at these. So I encourage you to, look at what I've got here and on the next page. Think through. Make sure you can sort of think through the details. Always feel free to come to office hours if you get stuck on any of this. But it's basically just clever tricks. So take a look at that. Okay. All right. 1.6. Y'all may already have seen all of it. I used to start this class by going into 1.6 first, just to get it out of the way. It's mostly linear algebra. Y'all have all had a course in linear algebra. But this is arguably maybe more of a geometric take on linear algebra than, depending on which section of 218 you're in, you might have seen a more algebraic sort of, matrix-oriented type point of view. But this is, in fact, all linear algebra. Just make sure you read through all of that. I am going to hit a couple of highlights. Here's one of my nominations for most underappreciated facts of matrix algebra. A lot of people think that the way to think of a matrix vector multiplication is you do a dot product of the rows of the matrix, then you dot with the sort of the column vector, and those dot products give you the elements of the matrix vector product, and that works if what you're interested in is performing arithmetic. And in some settings you do need to perform arithmetic. If what you are interested in is relating objects to other objects and making geometric connections and stuff like this, which is one of the things we're going to be really interested in this class, right? Then I think this point of view is actually better. Now again, computationally, this is a little bit more awkward. But as connecting ideas to other ideas. I think this is really, really nice. So it is in fact the case that if you know the columns of your matrix and you want to multiply that matrix times a vector where you know the coordinates of that vector, then the matrix vector product is a linear combination of the columns, and specifically it's a linear combination where you use the vector itself to make your coefficients in that linear combination. And I think it's really useful. Again, when I first started learning about matrix algebra and related geometry and this kind of stuff, I learned the dot product point of view. Probably all of y'all did too, right? Because again, in most of these introductory settings, the focus is on computation, right? But this was a revelation to me. I was embarrassingly old when I first learned this. I was probably well into my math major, and somehow I didn't get the memo on this. And I think this is really, really, really important, because what that means is that these column vectors, not only are they, algebraically significant, blah blah blah, they are geometrically significant. Everything that you produce when you multiply a matrix times a vector will be a linear combination of those column vectors. That's useful to know. Right? Those are the vectors that will span your outcomes when you do that multiplication. So I like to emphasize that. Again, you may have seen it before. If so, cool. If not, really good that we touch on it, right? I think everyone needs to know that. Okay, linearity. Now again, y'all had an entire course in linear algebra. I know that. I know you've seen this equation. I just think it's important to emphasize. I have been told by Math219 instructors that they feel like too many of their students get into Math219, and then the instructor says the word linear, and someone says, "Well, what does linear mean?" Right? Well, it's one of the fundamental ideas of linear algebra. Right? So we got to make sure we're very crisp in our minds of what does the word linear mean. And so linear, in describing a function, specifically a function from one vector space to another vector space, we're going to keep it Euclidean in this class. Is that true? Almost everything we're going to do in this class is going to be Euclidean, Rn to Rn. Okay. But in this, for such a function, linear just means this right here. You could do the linear combination before you plug into the function. You could do the linear combination after you plug into the function. You get the same thing either way. And there's equivalent formulations down here, of course. So anyway, very important to have this takeaway. I'm also going to talk about a few abuses of language. A little bit of an abuse, the way I've used the term linear here. The way people describe what I've written on the board here is very often abuse of the term. So this fact that this function is linear, very often people will say dot products are linear. Now that's an abuse. Dot products are not linear. Dot products take in two vectors. You gotta have two vectors to do a dot product. That is not what this is saying. I'm not saying the dot product itself is linear. What I'm saying is that if you fix some vector, we've already talked about this in relation to cross products, but if you fix some vector, and then if you say, look, here's what I'm going to do. I'm going to go around doing dot products with that vector. A is fixed, right? It's not changing. I'm going to take that and I'm going to go dotting that with whatever vector you give me. I'm going to dot it with A, right? This action, what I am doing to this vector X, if you think about it, the act of doing something to an input to produce an output, that's what a function is. right? So the act of dotting with a fixed vector A is a function. And when we sloppily say that dot products are linear, what we really mean is that this function, the act of dotting with a fixed constant vector, that resulting function is linear. Everybody see what we mean here? Yeah.
Doesn't a dot product create like a scalar though?
Absolutely.
And then
Yep.
we define function t as something that turns a vector from one dimension to the other. So how
Sure.
can that both be?
Scalars are vectors in one dimension. Yeah. No, it's it's one of these things that you have to kind of wait a minute. Does that make any sense? You know what? Technically, yeah, I guess that works. But yes, absolutely. Anybody else? Yeah.
So P here is a scalar?
No, P is a function. A is a... I'm sorry. Very often, this is another sort of an example of what I'm going to call an abuse, but it's very, very common. Very often we conflate a function with the outputs from the function. Yeah. And then in different contexts, you would absolutely never do that in a million years. So I was thinking in the other sense. No, yes, the outputs from P are scalars, absolutely. Yeah. But I think it'd be a little bit more appropriate to think of P itself, though, as being a function. Yeah. Okay, so likewise for cross products. This next one's a little bit weird, and I think this is worthy of discussion. It looks like I'm saying that D is determinant and D is linear. Doesn't it kind of look like I'm saying determinant is linear? And let's be very clear about this one. It is not. Determinant is not linear. Determinant acts on a matrix. If you add two matrices, their determinants do not add. Right? So determinant is not linear. What I'm saying here is not that. What I'm saying here is if you fix a few vectors, let's see, here we go. If you fix various vectors R1 through Rn minus 1, and then if you create a function, my function D is kind of like this. D says, look, whatever X you give me, I'm going to put it there, and then I'm going to perform this calculation, right? All these vectors are fixed. All these first n minus 1 row vectors are fixed, and the fact that I'm going to be eventually taking a determinant, that's settled. The only thing that you can do when you give me an X vector is it sort of completes the matrix that we're going to take a determinant of. Right? This function, not determinant that acts on a matrix, but determinant with the understanding that the first n minus 1 rows are this, and then thought of as something that acts on this final row. That is linear. Determinant itself is not linear. Does everybody see the difference? So, I mean, now how do people talk about this? You would think, right, based on what we talked about with cross product and with dot product, that people might just go ahead and, we'll be sloppy about this as well. We'll commit a little bit of math crime, and we'll describe we'll describe determinant as being linear, and it's just, it's too much of a math crime. Nobody says that, right? So you can't go around citing this as determinant being linear. It's really importantly not. But they do have a term to describe. This is, in fact, kind of a cool property of determinant, that if you fix certain rows and think only about one row being allowed to change, and oh my God, you have this linear. How about that? Isn't that weird? They call it multilinear. Side note, this works in any row. It also works for any column, right? So this feature of determinant is called multilinearity of determinant. Really useful fact. Okay. Okay. Sorry. Go ahead.
So you're not performing any action with the determinant. You're just saying it's just like the x vector is just going to replace the row or column, whatever it is.
The x vector. Yeah. So if you give me a vector x, and you say I would like to apply this function d to that vector x, then here's how that's going to work. I'm going to say, okay, that x you gave me, I'm going to put it right there, and then I'm going to say d. The act of performing the function d says, put all of that on top of that x, and compute. And when you compute all of this right-hand side, that will give you a number.
Okay.
And that's what d does to x. You give me an x, I do all of that jazz, and out comes a number called d of x. Right. Yep.
And that number would be the same if you placed the x in a different row?
No. It would be a different. That's a great question. If you define d by putting the variable vector in a different row, then you do get a different function. It would still be a linear function, but it would be a different linear function. Yeah. Right. In fact, y'all may recall when you switch rows when you're doing a determinant, there are predictable rules about what happens. Right. So think back to linear algebra and all that business. Yeah. Okay. All right. Yeah, so here's another one. Top 3 most important theorems from linear algebra, in my opinion. Certainly from the point of view of, how are we going to use linear algebra in this class, this is probably number 1 most important thing you need to know about linear algebra in this class, is that when you have I'm going to say Euclidean, of course, right? That we're just not going to get too far into abstract linear algebra. If you have a linear transformation, then that linear transformation can be written in the usual way with a matrix. To say it in streamlined, what's going to roll off the tongue nicely, every linear transformation is a matrix. Right, so really important fact, but it's even more important than this. Not only is this saying every linear transformation is a matrix, but if you look at the proof of this fact, we actually produce the matrix, right? So I want you to know 2 things. First of all, every linear transformation is a matrix. Really, really important, right? But also, given the linear transformation, the way you find that matrix is by this formula right there. There's an explicit formula for what that magic matrix is that describes your given linear transformation. And what that formula is, well, golly, that's going to be important. That formula, which, by the way, you'll notice that formula is just saying that the columns A are computed by these formulas. All it is that the columns of the matrix are the images of the standard basis vectors. This is very, very important little phrase that you should have drilled into your heads. If you hear someone say the columns of a matrix, then in your mind you should instantly hear are the images of the images of the standard basis vectors. That should just be a knee-jerk reaction. Question.
What's the backwards E in the second line of the page?
Let's see. So further up.
Yes.
Oh, you see, that's that shorthand again. You may recall we talked about this last week at some point, but that's the mathematician shorthand. It just means there exists. Yeah. Stuff like that I'm going to probably be using, unpredictably, riddled throughout the semester. Yeah, absolutely. All right. Okay, so really important formula. I want to point out why. I mean, a couple of quick, easy examples. If you want to, for example, find, let's see here, do I have to, Let's see what I can do here. If you have Rn here and you want to find how to write a rotation, I want to be able to rotate counterclockwise by some angle around the origin. How would you come up with a function that will execute this rotation? And the first observation to make is it's a linear transformation. Second observation to make is therefore it's a matrix. Third observation to make is not only is it a matrix, but it's a matrix where I know what the columns are, and all you gotta do is take the standard basis vectors, E1 and E2, in this case, because we're in 2 dimensions. You take those standard basis vectors, you do whatever the linear transformation is. In this case, it's a rotation. So just take these vectors, rotate them by whatever the appropriate angle is. And whatever those resulting vectors are, right, these results that you get from rotating those vectors, those are your columns for the magic matrix that will execute that rotation. All right, so there's a little bit of trig. You gotta, do the appropriate trig to figure out what these blue vectors are. But that's how you write down a rotation matrix, and it comes straight out of this theorem that not only is every linear transformation a matrix, but this is the matrix, and the columns are the images of the standard basis vectors. Y'all have a good day. See you on Friday.